Here's a plot of the carrier mobility measured in centimeters squared per volt seconds as a function of the different things that we've done to it. Our goal actually is to get to 60 or above centimeters squared per volt seconds. Okay. Now, most TCOs, when you deposit them, like azo, for example, is around here, about 10, 15 centimeters squared per volt seconds. That's horrible. It's absolutely horrible. It will not work. In fact, I probably shouldn't even tell you this, but we would prefer that our competitors continue to use azo for that reason. But it is a horrible TCO for that reason. Transmission suffers. So if we pulse the needle, on the other hand, the mobility moves up a bit. No surprise. It goes up to 20, 23 or something like that. But it will never get to the highest mobility that we need. If you make a special azo in which azo is aluminum doped zinc oxide or any kind of zinc oxide, if you make a special one in which you make a single crystal, the mobility goes up to about 44. That's the highest I've ever seen. I know because we've done that. Extraordinarily difficult. So what we've done is develop a new type of TCO in processing. We shot it up to about 50, and we increased processing better and better. And now we're at 84 centimeters squared per volt seconds. And the sheet roll is at less than 9 ohms per square, and the transmission in near infrared at 1200 nanometers is greater than 86%. We believe we can get that up to 90. By the way, these numbers are based on as a reference to air. Okay. Now, I should point out one more thing, and that is, and this has to do with the cadmium issue. There's a TCO out there that I absolutely love, and it has a carrier mobility on the order of 100 to 200 centimeters squared per volt seconds. It is based on cadmium oxide. It's a great material. I think NREL developed that. Cadmium oxide or doped cadmium oxide or cadmium zinc oxide. Those are great materials. The mobilities are very, very high. But the problem is with the cadmium. So we tried it. It works great. We get great results, but it has cadmium. It's a very thick layer of cadmium, no less. So that's a problem.
Sorry.
Yes?
So you're showing an 86% transmission. Is that for a single film or just stacked?
It's just a TCO. It's just a TCO in the near infrared at 1200 nanometers.
So when you're stacking 3 of these to do your tandem structure, that means you're getting 65% or so.
I'll show the calculation in the very next one. Thank you.
Where does indium oxide fit in again?
Indium oxide actually, by itself, would get higher mobility in general than zinc oxide-based materials. But ITO by itself does not do it for you. Yeah. And the other problem is that indium oxide has a different lattice structure than zinc oxide, and that's part of the reason behind it. But the other problem is that it has indium. We already use a lot of indium already, and so there's an issue with the cost. We've been able to negotiate long-term contracts to bring that down for us. That's a good question. Currently, no AR coding.
So that's
reference to air.
Yeah,
right.
You're not doing any correction then, so that the reflection from the coding is less than
Yes.
5% or so.
Yes. Yes. So moving on, this is a transmission spectrum that partly answers as far as your question here. This is reference to air as well. So a typical TCO looks like this. All TCOs transmit very well in the visible because the free carrier absorption is in the near infrared. I believe it goes as lambda to the third power or something of that kind. It'll kill you. Right? But in the near infrared, where you need to have highest transmission to the bottom device, it drops significantly. This is a typical TCO. I won't tell you what it is, but sorry, but it's about 51% at 1200 nanometers, where the band gap is the lower of the bottom device. So at 51%, you have 2 TCOs, so 51 times 51, that's 26% transmission. Right off the bat, you've lost 74% of your light. If you do nothing else, you've just lost the game. Right? Yes? Actually, that's a great question. We're not using soda-lime glass for that. We're using what's called water-white glass. Yeah, because it turns out that in nature is very, very cruel, because it turns out that soda-lime glass is very inexpensive, but it contains iron. And iron has an absorption right there. Right there. So we use water-white glass where the iron is leached out. It's a little bit more expensive, but when we go to high volume, they're comparable. So again, if you are at 51% transmission, which is typical TCOs, you're losing 74% of the light. If you're at 86%, for 2 of them, you're at 74% transmission, which is significantly better, but it's still not great, right? you're losing 26% of the light. But that's enough to get to the high efficiency that we've been able to achieve. So again, we've been able to get to very high transmissions in the near infrared with low resistivities because of the carrier mobility. Now, another point here is that in chalcopyrites, you have to process the film at very high temperatures and in very corrosive environments. But as you know, all thin films, if you deposit them at very high temperatures, they generally tend to do much better because of the effect of the annealing that occurs. Well, unfortunately, the TCO is in the bottom of the absorber, and you have to protect the TCO somehow or prevent it from being degraded. And in our case, we process at 550 degrees or higher in a very corrosive environment. Again, I apologize, I can't tell you how we do it, but we were able to solve this problem. It's a very difficult material science problem. It may allow us to put the absorber on top of this TCO without degrading the TCO. We can still maintain less than 9 ohms per square with high transmission. So here's the net result. This is the top absorber, and I'm going to spend a little time explaining what's happening here. In a standard two-step process I just described to you, the absorber looks like this. Notice that there are a lot of voids there. Keep in mind how we did this, right? We deposited down thin film metal precursors, and then we reactively annealed it, which means that the reaction surface is on the top of the precursor layer. So in order to have that reaction occur, there has to be mass transport from the bottom to the top. That, in part, explains why there are voids there, because you have to move material from the bottom to the top where the reaction occurs. The second reason is that it turns out that going from metal to semiconductor, there's a lattice expansion on the order of 2 to 3. And so that's another problem as well. Now, this is a single junction device. Oops. This is a single junction device on moly. So we don't have to transmit light. All right, this is the bottom device. So the voids don't matter to us. What really matters is that can the efficiency be very high with those voids? It turns out you can. The efficiency can be extremely high, even with voids there. What do the voids? What's the disadvantage of the voids? It's the delamination that can occur. So it's a right balance between efficiency and the delamination issue. However, on the other hand, if you're making the top absorber this way, these voids constitute a significant light loss problem. We have to get rid of these voids. If you have these voids there, you will never make it. Okay? So, as I mentioned, we have developed a new, a different absorber formation process, and this is the SCM from that process. This is roughly a 2-micron thick film on top of a TCO, and what you see is that the grain sizes are enormous. They're on the order of 1.5 to 2 microns even thicker, but the voids are completely gone. The increase in the transmission is dramatic, and I'm going to show it to you in the next slide. But this is an extremely important problem to solve if you're going to get any type, if you're going to extract any type of useful efficiency from the bottom device. If you don't do this, then don't bother making a tandem. So this is the transmission of the entire top device. And this is a spectrum taken by NREL. You can see that band gap is near 1.6 something eV, and near 1,000 nanometers is about 70% transmissive, and near 1200 it's about 60 or so % transmission. That may not sound like a lot to you, but typical tandems that you see out there are in order of about 20% transmissive in that region. So we are over 3 times more transmissive than the others. So having said that, I just described to you then the structure, the materials, and how we put them together. Now the last remaining step is we have to scale it up to full-size modules. Actually, let me back up. Let me show you what the performance looks like for the 20 by 20s. This is a 20 by 20 centimeter squared tandem. It's 20% efficient. And these are the IV curves for that. The top device is at 13% efficiency with a VOC per cell of 840 millivolts. A quick perspective on that, for silicon, the VOC tends to be on the order of half a volt. The JSC is about 22.6 milliamps per square centimeter. It's higher because it's high, but it's very close to the limit for a wide band gap of that kind. And the fill factor is about 68, 69%. That's a 20 by 20 device. The bottom device, we've been able to extract 7% from the bottom. And actuality, we're prouder of this result than the top device, because extracting that much efficiency of the bottom device was key to getting to high efficiency. Most people get about 1 to 2% at most from the bottom device. I made a comment here, and that is that, as you saw from the previous slide, we can still improve the amount of efficiency we extract from the bottom device by eliminating even further the free carrier absorption. If we make a cell out of that, it's 22% efficient. And again, we're getting 14.2 from the top and about 7.8 from the bottom. We're particularly proud of this one.
How long are those cells?
About a square centimeter. So if you look at the EQE spectrum at this point, the external quantum efficiency, what you see is this. This is the external quantum efficiency plot for the top device, and this is for the bottom device. I don't know about you, but this looks gorgeous to me. It's very difficult to do this, right? I mean, the ideal case, this looks like two rectangles, right? And we can't get two rectangles. This drop-off here is because at the time we were using cadmium sulfide as the emitter for the top device. And so the band gap is a little bit low, so you see a chunk being taken out of that. But the first thing to notice is that the contribution from the top and the bottom device is quite good. There's a good contribution from the top and the bottom. Another thing to notice is that the onset at low energies is very sharp, particularly for the top device. And that's important because it tells you what the it tells you that we're extracting as many of the carriers from the back of the device as possible. Excuse me. Okay. So now let's move on to how we're going to scale this up to full-size panel, or where we stand with that. Let me start with the bottom device. Okay. As I mentioned, our Gen 1 device, our Gen 1, which is a single-junction SIGS device, is in production in Hattiesburg, Mississippi. And the line there is our first line should be at about 150, 200 megawatts. We are not at full capacity because of the obvious reason of the marketplace right now. Nevertheless, our champion module, the champion module efficiency as measured by NREL, is 14.8%. The corresponding circuit efficiency is 15.1%. This is a full-size module, SIGS, at 1 square meter, 65 by 165 centimeters squared. Since then, we've demonstrated a circuit efficiency of 15.8% at full size, and we're getting ready to submit that to NREL as well. And we've developed a near-term roadmap to get to 15+% efficiency at the module level. Our target is to get to 16. Okay. Now, to scale up the Tandem, there are tremendous challenges to that. The most important happens to be the aerial uniformity. That is almost everything to make this happen. And so how do we approach this? How do we mitigate the risk? Well, we do this as time in phases. We scale up, we do this in a controlled, stepwise fashion. As we develop new types of materials, which we had to do with this, we start out at the research level at 5 centimeters by 5 centimeters. And then we move that up to, we scale it up to a 20 by 20, which is where we are with the Tandem currently. And then we scale up to a full-size panel. And what's important is that along each step of the way, we use analogous equipment to ensure that the scale-up is done properly. We would not use different equipment along the way, but that would not be the right way to do it. So, for example, we use sputtering. We use furnaces. We use all the same type of things, only just bigger. So this particular method of doing that has worked very well for us in our Gen 1 product, which is, again, as mentioned, is production currently. And because the Tandem uses roughly the same type of processing, we have great confidence that we can scale this up properly as well. So here is our first full-size, actually it's our third full-size Tandem module. This is standing next to a canonical person. You can see that canonical person standing right there. And I believe this is the first fabricated this size. It is a full-size Tandem module. The efficiency is not 18% or 20%. Yes. Since this is thin films, we blanket cover the whole thing, and then we define cells by laser scribing. I didn't go into that because it will take a long time to describe that.
Will you comment on the size of the substrate glass itself when you describe it?
Yeah, actually, the substrate glass itself is it's a little bit bigger than 65 by 165 centimeters, so that active area is about 1 square meter. Right? Yeah, so what we do is we have a large panel, and then we deposit the bottom contact, and then we laser scribe what's called the P1 scribe that helps us define the actual cells. The P1, as you know, is an isolation scribe. Then we put down the absorber, the emitter, and we do a P2 scribe. That's a via hole, essentially. and it would put down the top TCO and do a P3, and that's another isolation scribe. And that's how we generate these different cells, which is that's a good question, but it's very different than making wafer-based systems in which you have to make individual cells, and then you string and tab them together, which is extremely labor-intensive. Right? So we blanket cover the whole thing, and then we scribe it. And the scribing is very, very fast. So finally, I just want to show this because a tandem, full-size tandem is not twice the size of a single junction device. It weighs roughly the same. And that's important because from a labor perspective, we don't want to get much above 40 or 50 pounds because of the difficulty of having two unionized people up on the rooftop doing this, right? So finally, I'd like to end by saying that this is our facility in Hattiesburg, Mississippi. It has a capacity of 500 megawatts. We have one line in there so far. We are looking to get 3 lines in there. It is a Class A manufacturing facility that's expandable to 700,000 square feet. Again, this is in Hattiesburg, Mississippi. You're probably thinking, where the heck is Hattiesburg? We went there because of, actually, I probably shouldn't go into that right now. But anyway, we're at Hattiesburg. And if you're ever in the region, I invite you to come by. We will be glad to show you around. It is impressive. You could play football in there many times over. You can get lost in there. You can die there. No one would know. All right? Not that has happened. Anyway, this is the extent of it. I'd like to end by saying that at Stein, we do a lot of very interesting work, everything from very fundamental research all the way to some very challenging engineering work in designing modules, systems, and so forth. So we are always interested in bright young minds, young or otherwise, it doesn't matter. And so if you're interested, please come by. We are looking to hire a few select people at this time. So if you're interested, please come and talk. Or if you're interested in a tour, please come and talk to me. I'll be more than happy to give you a tour. If you're in Hattiesburg, someone else will give you a tour. I'm not often there. Our headquarters are in South San Jose. So that's it. I'm open to any questions. Yes?
So if I'm not mistaken, usually solar cells heat is through the bottom. You add an extra layer of glass, which is very low thermal conductivity material, and most of your power is from the top cell. Do you see significant thermal issues because of that extra thermal resistance series?
Actually, it turns out that, first of all, that's a great question, because we were worried about that as well. We modeled that, and it turns out that the combination of the breakdown efficiencies presents no problem to us. So in other words, we just use those 2 pieces of glass, and it is perfectly fine. But we were worried as well. Well, we test them at 25, of course. The actual temperature they operate at is something that I can't get into right now, but it's not 25.
Right. You're out in the desert, it's 45 to start with.
Yes, yes. Of course, you're referring to centigrade, not Fahrenheit. It turns out, though, that with chalcopyrites, the temperature coefficient is actually quite favorable. And for larger band-gap materials, the temperature coefficient is even better.
Yeah.
So we actually went out in that regard. So for example, if let's say you wanted to put a tandem in Dubai or whatever, we believe that it will work.
So on the cells,
Yeah.
there's some mismatch between the currents, so you're
Yes.
tracking those with 4 compounds.
No, we were.
That's those are in series.
Yeah, so the ones that are in series, we actually do something else to equalize the current, not the current density. So if you look at that, so the thing to think about is this. I'm sorry, I have to be careful how I say this. We're equalizing the current, not the current density. So if I told you that the cell widths are the same, that it immediately tells you what's going on, right? Well, they're not. So, sorry, I think my attorney is going to kill me at this point, but.
I think we already have an idea.
Yeah, I think so. I think so. You're all smart guys, right? And gals, and so on. Hey, do you have a job for me? I think I'm going to be fired tomorrow. Yes. How to reduce the free carrier absorption? It really, actually, what you really do is control the carrier density so it is it is acceptable, but in order to, so the way we do it is by increasing the carrier mobility. That's essentially what we do. And the reason why all other tandems don't extract very much from the bottom is because they're using the wrong TCOs. And I probably shouldn't have said that either, but that's the key thing. Anything else? So if you're interested, oh yes. In the production line? So in our factory in Hattiesburg, we fluctuate between 85 and 90+% yields. And that's not very good, actually, by the way. We want to get it so that we're firmly into the 90–95% yield range. I probably shouldn't have said that either, but nevertheless, that's the truth. Yes?
Have you done lifetime reliability assessment?
Yes.
How does that vary from the top zone to the bottom zone?
So actually, that's a really good question. We have not submitted the Tandem for IEC or UL certification yet. And because we have to submit, 60 full-size panels for certification. So we have not done that yet. So, but what we have done instead is, as we were moving along, we have been conducting our own reliability testing in-house, like 8585, for example, to make sure that we're not doing anything ridiculous. So so at the point when we fully scale up the Tandem, we will submit those for certification. Yes?
You mentioned that the ideal band gap for the bottom sound is between 0.9 to 1.1 dB.
Yes.
And you mentioned that the fuel you use is CIG/SSD.
Yes.
So I'm wondering whether is there any reason why you have to operate software like that?
Yeah. In part, actually, it turns out that the sulfur, that's a very good question. It turns out that the sulfur does a lot of things for us, one of which is it helps passivate certain surfaces very well. And another rather nebulous thing is that when we use the sulfur, it just works better. It's more reliable and so forth. And you think, well, why are we going to a quaternary when there's a quaternary? Is it warranted? And in this case, it is. Anything else? Great. Well, thank you very much. I really appreciate my time here.